Okay, so some geometry terminology to remind ourselves as we're getting back into the trig functions. So, big details to bring back. We have ideas such as the angle. An angle is composed of two rays connected at a vertex. And an angle specifically represents the space between them. So, as with many mathematical terminologies, they throw a bunch of English words at you, and then you're asked to figure out what the heck they mean. So let's talk about what these pieces mean, put them in context with a picture, and remind ourselves of a bunch of different pieces that come specifically from algebra. Let's take a look at the first part. Number one, it says it's composed of two rays. If you remind ourselves about a ray is defined as piece of a line. So remember, a line is defined as a straight segment that continues on in both directions to infinity. A ray is defined as a piece of that, with a starting place, referred to as a vertex, and a direction in which it is going. So in this case, this is one ray. Now other rays can be in other positions, can have the same starting place, could have different starting places, could go in the same direction, could go in different directions. What makes an angle is when they have the same starting place and they create a space between them. So if I put a second ray up here, they have to have the same starting place in order to create this angle in between them. And the angle itself is referred to not by the rays, but by this little space that exists between them. So this space here is how we define our angle, which we'll call theta. In trigonometry, there are four major Greek letters that are used for angles. If you were not taught all of these in geometry, I apologize. When I taught geometry, I didn't teach all of these either, because, quite frankly, many people don't take trig. But if you did not know, trigonometry is so old. They use a lot of Greek notation, especially when it comes to the variables, and that tradition has stayed for a long time. There are four Greek letters you're going to see throughout this year, and here they are. The first one, theta. It is illustrated by a circle with a line through it, indicating that this is representing an angle specifically. If you take a physics class, theta can be pretty common. Another common one that takes place both in physics and trig is phi, which looks kind of like a very strange, almost like a pitchfork, a very dead fish, I'm not sure. This is called phi. Depending on who you ask, it can also be pronounced phi. It's P-H-I. Depends on who you talk to and how bad their Greek is. We have two others. We have omega. Omega is W, where you loop the center. This is actually lowercase omega. Uppercase omega you may have seen if you are a fan of religious ceremonies. They often use omega. Sci-fi shows love to use omega. That's uppercase omega. We use lowercase omega. Kind of using lowercase x instead of uppercase x as a variable. And the last two, and yes, I said there are only four, but these two kind of go hand in hand. These are the most common ones. This is alpha, which looks kind of like a very strange little A. In fact, some people even just write A for alpha. I'm not going to yell at you too much for it, but I would correct you the first time I see it. It looks more like you've attempted to draw a fish and forgot how the tail works. And then beta, which looks like a B that somebody was too lazy to finish. So we have theta, phi or phi, omega, alpha, and beta. If you see any of these letters, it is an indication to you that is looking at the problem that they are referring to specifically an angle, nothing else. It is uncommon in mathematics to use these letters for anything except an angle. So when we talk about trig functions, we will often use one of these five. When we talk about pictures from geometry, we'll often use one of these letters, with theta being the most common. Okay? So again, you're not required to be able to spell the words. You're required to know what the symbols mean. So as long as you can draw an alpha and know that it stands for alpha, you're good to go. As long as you can draw the phi and know that it's phi, you're good to go. I wouldn't recommend sitting down and practicing all these, but Greek alphabet's pretty neat. I'd recommend trying to take a look at it at least once. The Greek alphabet has a lot of similarities to our current alphabet, but it's not all the same. For example, the Greek letter rho is a P. P. Rho, P. It makes sense, sort of. Not really. So, we need to talk about, as we discussed, angle, ray, and now we have a way of talking about the angle itself. So in this picture, I can call this angle theta, I can call it alpha, I can call it beta, I can call it phi, I can call it omega. Any of these is an acceptable name for this particular angle. And then, of course, I can also go back to algebra. I can call it x, I can call it y, I can call it z. I could get really extreme, I could call it smiley face, Friday face. The artist formerly known as Prince. Probably too young for that. It's okay. But again, the angle is the space in between them, not the sides. It is a measurement of how much space these two rays are taking up. And in geometry, we talk about how there's two different ways to measure this. You can measure what's called the interior angle, which is the small space in between, which I have indicated here. There's also something called the exterior angle, which is indicated by the outer piece, what exists on the outside. So again, because the word angle is so loosely defined as the space between, we can either measure the short distance between them or the long distance between them. And both are an accurate name for this angle. But we would never call them the same thing. I can call one theta and I call the other one alpha. But I don't want to use the same letter because that would imply they have the same value, which based upon the picture, they clearly do not. One is clearly significantly larger than the other. Now, as we discussed, there are multiple common angles and now common radians. You have things like the 90-degree angle, a right angle, which we've also called pi over 2 as the radian version. We have the straight angle, which we call 180, or pi. We have a full spin, which is 360, or 2 pi. But again, the idea of the angle is it's a calculation of the space. We apply a number to them, specifically so we can compare them. An angle that is 50 degrees should be slightly larger than one that's 49, and slightly smaller than one that's 51. They have a relationship between their size. But again, it's about the space. In theory, this angle, which I've drawn with two fairly extended rays, is the same size as one that I put over here, but use very short rays. Because of how the rays work, the rays keep going, so too does the space keep going. So the angle itself always has these unique properties. They fill in the space in between them. Now, some terminology. We have the rays themselves. In geometry, we usually apply letters to these rays. This is less common in trig, just because we're more focused on the angle itself, not the pieces that make it up. But some terminology to know. This little part where they meet together is always referred to as the vertex. It is the place where the two rays meet. In most situations, this is the place in geometry that mattered a lot. You did most of your math using the vertex. You cared when you were drawing where the vertex is. It's the piece that was most important. Now, unlike in geometry, we focused upon shapes. Everything in geometry is focused upon shape math. The word geometry itself stands geo, which means shape, metry, which means geometry, which means shape, math. Trigonometry focuses specifically on angular math. A lot of lower level teachers will tell you that it stands for triangle math, which is partially true, but not really the same thing. Because in our cases, we're talking about angles that can be much, much, much bigger than anything you can find in the shape. If you're talking about a skier going down a hill, and they do a cool little flip trick, and they spin, 1,120 degrees, you can't draw a shape that does that. It just doesn't exist. You can't draw some fancy triangle that's got 1,120 degrees. It doesn't work. Because as we talked about before, this cycles. We start at 0, we continue around till we get to 360, we continue around again, we get to 720, and we keep going around until eventually we get to a terminal spot. Place where the angle ends. Now, in trig, the angles we will talk about, and the angles we will focus on, and the angles we will draw are always drawn the same way. Unlike in geometry, where you can have different shapes and different positions, you have to talk about things like congruency. Ooh. similarity. Ooh. All these different terms and definitions to remind us that angles relate to each other. In trig, we say no. We are going to focus upon one style of picture to make it super easy to talk about the angles. Because if all we care about is the angles themselves, then we don't really need to have those other components. So here's the next piece. When it comes to the picture itself, all angles in trig are drawn on a grid, similar to what you would do in algebra class. And we've already talked about the unit circle in this class, so this should look rather familiar. All angles are drawn with one side resting along the positive x-axis. So our ray has a vertex that is the origin. So we have our vertex here. One side is listed on the x-axis in the positive direction. This is referred to in mathematics as the initial side. Why is it called the initial side? Because it's where we started. Initial means starting place. Where the angle ends, has a name as well, is called the terminal side. So if the angle goes up in here and to the left, this is called the terminal side. And remember, the angle we're talking about is this space that exists in between them. So in this case, the picture we're looking at is this space, not the red lines themselves. The red lines themselves are just there to define what that space looks like. It is the green space in between that we define with the angle. We might say it is 145 degrees or 120, depending on its location. But again, we define it using these few terminologies. It's an angle, and in trig, this means that every 45-degree angle looks exactly the same. It'll have the same initial side, the same terminal side, the same vertex. So unlike in geometry, how you have to constantly readjust your pictures and, oh, it's facing this way now, that makes it look different. No, we don't care. Trig does not have time for that. All angles are drawn this way. Unlike in geometry, we'd have, say, ooh, we're dealing with a 30, 60, 90 triangle. We have to draw it in this direction. No. It will always be drawn with its terminal side here, its initial side here, its terminal side, where that angle is supposed to be. You will never see it start to the left, because that's not how trig focuses. In trig, our goal is to focus upon comparing angles and doing math with the angles. So rather than having angles being all over the place, we said we will do everything this way. Does that mean you couldn't do it a different way? Of course, you could have the initial go way up and down. Or you got to go to the left. Of course you could. This is just the agreed upon way. We sat down as a group and said, you know what? This is how we're going to do it. Let's all agree, and let's all move forward. Okay. Next. Oh yeah. Because of how this is done, the next terminology we talk about is what's called quadrants. Now, you may have talked about quadrants in your Algebra 1 class, but we've all slept since then, I hope. Quadrants refer to the location in the grid. In algebra, in geometry, and now in trig, there are 4 quadrants. The first quadrant is in the upper right-hand corner, quadrant number 1. In this quadrant, all the x values are positive, all the y values are positive, and so it's common to draw the first quadrant using this notation, plus, plus. Remember, the parentheses represent a point, and so if you're in that first quadrant, the first value, which is the x value, is going to be positive. The second value, which is the y value, will also be positive. And we can see that if we look at our unit circle. Going to our unit circle, the first value for each of these, positive. The second value for each of these, positive. That's what makes it in the first quadrant. The first quadrant has a special property. Now, as you can see, as we draw our angles, they continue going counterclockwise, which means next quadrant, quadrant 2, is right here. Quadrant 2. Quadrant 2 has slightly different properties. But again, they're the same properties of algebra, right? Because it's to the left, the x values will be negative. Because it is up, the y values will be positive. which means that even if you know nothing about the size of the angle, if I tell you it's in the third quadrant, we know what it's going to look like in some way. With quadrant 3, it's going to be down here. Because it is quadrant 3, it will have always very specific properties. Because of its location, it is to the left, it is down, which means that it will be notated by negative, negative. And again, on our unit circle, we see that. Every x value in that quadrant is negative. Every y value in that quadrant is negative. And finally, quadrant 4 is plus minus. So again, every angle that exists in each of these quadrants has similar properties. Not exactly the same properties, because again, they're different sizes. But it'll always have similar properties. First quadrant, its values will always be positive for both the x's and the y's, which if you think about from what we talked about with the unit circle, that means that the cosine values will be positive. The sine values will be positive. Remember, when it comes to that unit circle, x means cosine, y means sine. Which means each of these quadrants, we can make predictions about what the angle is going to do, knowing nothing about the angle itself other than roughly where it's at. If the angle is in the second quadrant, then I know for a fact the sine value will be negative. Sorry, I always did it backwards. The cosine value will be negative. The sine value will be positive because of its location. Which means if my number is between 0 degrees and 180 degrees, I can tell information about it based upon its location. If it's in the first quadrant, it's going to act one way with its values for the sines and for the cosines. Second quadrant, same thing. Third quadrant, fourth quadrant, I can make predictions about what the values are going to do, whether they're going to be positive or negative, with just where it's located in terms of the quadrants. Again, this is discussed very small amount in algebra about things like the sign and how to name the quadrants. Angles are discussed in geometry. Trig puts the two together and says, okay, because we're identifying our angles always the same way, always with our initial side here, always with our terminal side somewhere else, because of how we're forcing them to be built every single time, we force them to have properties every time we build them. So every 60-degree angle will always end up in the first quadrant, and therefore will always have a positive cosine and a positive sine. Every 230-degree angle will always end up in quadrant 3, meaning we'll always have a negative cosine value and a negative sine value. Because we have forced it to always match this perspective, it maintains properties no matter how big it is or how small it is, whether it's positive or negative, whether it's bigger than 360 or less than 0. We'll always maintain these properties because of how we have strictly built it. Now, the last thing I want to talk about is if you're asked to draw angles, there's simple ways you can do it. I'll reference the unit circle a bit, but it's actually pretty nice to be able to do it by hand. You were probably taught in geometry, at least for a short time, how to draw angles with something like a protractor. You know, the little circular device. It's got little angle measurements on it. You gotta line up the dots. It looks all cool. Yeah, we don't do that here. We're not as concerned with perfection because in geometry, you're trying to do things like prove congruence. So you have to be very, very precise. You're trying to prove similarity. So you have to be very, very precise. Here, the math is going to work out because of how it's located in the picture, not because you're very precise with it. So if you happen to draw a 130-degree angle that's like 3 degrees off, the math will still work out. You just have to do the math correctly. We're not worried about being super precise. We're worried about things like, hey, what quadrant are we in? Is it close to one of the values that we have in the unit circle? Those kind of things become super important. And so when it comes to drawing an angle for this class, I'm going to go through the basic steps. And this will be where we finish out for the day. Okay, unlike in geometry class, where I'm demanding you buy a protractor or supplying one, we don't do that here. Okay? Because we are forcing it to always have this same setup, we can cheat a lot of this stuff. First, to draw an angle in this class. Start off, don't draw an angle, draw the grid. Just like as if you're graphing something for algebra. Let's see here. Luis, give me an angle. Keep it a degree one, keep it simple to start with. Make it sure it's between 0 and 360. But give me one.
240.
240. Beautiful. So Luis wants to draw a 240 degree angle. Here we go. Step 1, draw your grid. Boom, done. Step 2, where does the initial side go? That's not a question. It's a demand. It goes in the same place every time. Where does it go? Left to right. Beautiful, I know. It's beautiful. All right, next piece, it's got to be 240. So my next piece of my ray has to be at where 240 is. Now keep in mind, it's going to go, because this is a positive number, it is going to go counterclockwise. So for you guys, this way. As it is going counterclockwise, I already know some of these locations. I already know straight up and down, for example, is 90. I know here is 180. I know here, 270. Here, 0 degrees or 360 degrees. What I can do is, I can play a little game. Let's get close. Right now, I know for a fact that my number is 240. That's bigger than 90. So that means it can't go in the first quadrant. It's bigger than 180. Can't go in the second quadrant. Between 180 and 270. So it's got to go somewhere in here. What I can do is, visually, there's a couple things that you can do that every person should be able to try. Every person by now should be able to estimate where halfway is. And if we know what our math does, halfway between 180 and 270 would be 225. So I can ask again, is it bigger than 225 or smaller than 225? I can get it close. Again, if it's bigger, I'm going to go farther counterclockwise. If it's smaller, I'm going to go less counterclockwise. So in this case, I'm doing 240. It's bigger, so I know it to be somewhere in here. So I ask questions like, how much bigger? A lot bigger? A little bit bigger? I can even go farther and be like, okay, let me estimate halfway again. The goal is not to be perfect. The goal is to be close. This is not geometry class no more. I'm not sitting there saying, grab a protractor, make it precise now. No. Nobody cares. We want to be close because we want to be able to use properties to fix our solutions. So in this case, it's slightly bigger than 225. I'm going to guess and say 240. Is it close? Sure, good enough. So you got to be able to mentally take this thing and break it roughly in half. The second thing every person should be able to do, thirds. Thirds are great. Because of how these things are designed, we know that in this picture, thirds would break this into 30, 60, and 90. And again, the goal is to visually get close. If you're a little off, adjust. Remember, our goal is not sitting here to be perfect, although some of you, I'm sure, are those people that want to be perfect every time. Our goal is to get close. Visually, one skill that separates people who are in like kindergarten and people who are older is almost always the basic ones of like, can you look at a picture and tell where the middle is? As you get older, it's can you tell how to break it into thirds, roughly. Okay, we're not looking for perfect, we're not looking for precise, we're looking for close. And again, the unit circle contains both sets of values. Because the unit circle breaks into thirds to get 30, 60 to 90, and breaks in half to give you the 45. So every value that we've talked about on the unit circle itself can be found by breaking either something in half or something into thirds. And again, the goal is to get close. Okay, if the number, instead of being in degrees, Luis, thank you for that, if it's in radians, you can do the same process because it's fractions, it's a little harder. So if you're like most students, you probably want to cheat. Convert it into degrees. Degrees are usually easier to work with, when drawing them especially. because we understand the numbers much better, not fractional numbers, right? So convert it into a degree, and then use our estimation skills. But don't forget, if it started in radians, make sure you say it's in radians when you're done. If I say, hey, graph 7 pi over 6, hey, that's great. Make sure you write it, the answer, 7 pi over 6, roughly where that should be. If you use degrees to get the solution, that's fine. If it is bigger than 360 or 2 pi. So we talked about these are coterminals. It's a fancy word for it.
Yeah, that's a new one.
So remember, coterminals are those that are either bigger than 360 or smaller than 0, or bigger than 2 pi, smaller than 0. So, as a reminder, coterminals. So, if we take a look at one that's really nice in the box, 60 degrees, the coterminals for 60 would be to either add 360 degrees or subtract 360 degrees. This creates a coterminal. So in this case, coterminals of 60 degrees will be ones like 420 and negative 300. Now when you're drawing those, because they are coterminal, they will look like 60. Example, if I tell you to come up here, let me get this back where I would start. I'd recommend every time, if the problem's in degrees, start with this picture. Every time. 0, 360, 90, 180, 270. And then break it in half, break it into thirds, whatever you need to do to find those other values and get it close. If the problem says, hey, I want you to graph 420. Cool. Here's how I do it. I know, because it's coterminal, it's going to go to 60. The difference, because I want to go to 420, it's not talking about this space. This space is only 60 degrees. To get to 420, I need to add a little piece of notation. 420 is located one spin to 60 degrees. So, take a look. If I just want 60 degrees, I can just mark my terminal side and my initial side, and I've got 60 degrees. Because that is 60 degrees. If I want to do one of the coterminals, I need to indicate somehow that I'm going either past the 60 to get to a new number, or going the other direction. So we use an arrow. The arrow indicates I'm going in a different direction or going past something. So if I want to go to 420, how do I do that? Well, I start by finding the coterminal, which is 60. I draw that one first. Then I indicate that it's 60 degrees after one turn. So I go one full turn around, and then continue up to 60 degrees. On the other hand, so up here in red, this would be how we would draw a 420 degree angle. Have I said 420 enough today? Is it less funny? No, it's still funny. If I said negative 300 degrees, which we just said over here, is also coterminal to 60. Because it is negative, it must go in the other direction. Which means instead of going counterclockwise, it's going to go clockwise. Squeaky squeak. This indicates that A, it is negative because it has gone in the opposite direction, but it still ends at the coterminal spot. It still ends at 60 because negative 300 is the same as 60. 420 is the same as 60. The question is, how do you get there? Do you get there directly? Well, that'd be 60 degrees. Do you get there by going one rotation and a little farther? That's 420. If I want to go the other way, negative 300, I got to go back around the other direction to get to 60. Another example, perhaps. Let's take a look.
Maybe you should do one of the ones that are on here.
I would be happy to.
Really?
Always.
Okay.
So like I said to you guys, I'd recommend if I say to draw angles in a homework problem or in a test or something, start here. And if it's in radians, just convert these into pies. right? We'd have 0, pi over 2, pi, 3 pi over 2, and 2 pi. But again, you can do the math in degrees if it's easier. Okay, what's one of the ones we have on there?
120 degrees.
120 degrees. Okay, there's this we want to do 120 degrees. I'm going to answer two parts of this. I'm going to graph 120 degrees like normal, and I'm going to graph two coterminals, a positive coterminal and a negative coterminal. Take a look. Let's start by going here. Let's redo our problem. So the number we have now is 120 degrees. So I can add 360 to get to a new coterminal. I can subtract 360 to get to a new coterminal. I'm a little rusty
So
today.
you're going to add and subtract 360 every time. Okay.
And if I want to have two coterminals, I just add or subtract it again. So I either add another 360 or subtract another 360.
So if you get 120 plus 360, and you get
480.
480, yeah. Then you take another 360 and add it, and that's how you get two of them. Okay, and that's the answers? You don't have to do all the graphing stuff?
Not until this section.
Okay.
Okay, I can also subtract 360. Subtracting 360 would give me an answer of negative 240. Let's talk about how to graph these three angles. So first one, I'm getting way too many markers here. First one, the 120. So again, my initial side does not change. The initial is always here. If I want to do 120, I can estimate. So I can go up here and say, okay, it's bigger than 0, bigger than 90, smaller than 180. So 120, I can break it into thirds. If I break it into thirds visually, 120 is one of the thirds, which makes it super nice. So I would make this 120 degrees. Again, my goal is not perfection. If I wanted perfection, I'd give you something to make it perfect. I'd tell you to do it on a computer. If I wanted perfect, I'd get perfect. I don't want perfect, I want it close so we can visually use those skills we saw up above to ask things like, will sine be positive or will sine be negative? Will cosine be positive, will cosine be negative? Those kinds of questions are what we're looking for. Now, if I wanted one of the coterminals, I'd have to make an adjustment. In this case, purple, 480. There's 120. If I wanted to do 480, 480 is coterminal to 120, so it's going to end in the same spot. The difference is it is one spin farther. So again, it starts on the terminal side, where it began. It'll go past it, continues on, until it gets to the coterminal. This is how we would measure and draw 480 degrees. Notice we can't physically draw 480 because we have only between 0 and 360. So how do we show that it's 480? We show that it's coterminal 120 after one spin. The other one, negative 240. So again, I know where negative 120 is, or positive 120, but because it's negative, it has to go in the other direction. So again, I start at the initial side, that's why it's called the initial. I would go simply in the other direction. This one here in this awful brown color is negative 240 degrees. So 480 is the one in purple, one spin over to 120. Negative 240 is in the opposite direction over to 120. And then 120 is, of course, just right there. This is how we can show incredibly large angular values without needing to draw really big complex shapes, which we know is impossible. We instead just use the same system and do it with coterminals. If I want to draw 1,000,000 degrees, I don't draw 1,000,000 degrees. I figure out where 1,000,000 degrees is going to be, put my line there, and just spin until I get there. It works. It'll look a little psychedelic at the end, but it works. Questions? The first few homework problems we have is drawing angles. London?
Yeah, do you want to assist me on these last few?
Sure. Hearing others, I'll go ahead and stop the recording and go.